Okay, in this video, I want to talk about finding multiplicative inverses of square matrices by using Gaussian elimination. Okay, you remember in a previous video, I showed you how to find the multiplicative inverse of a 2 by 2 matrix by using the determinant. And that method does generalize, but it's kind of complicated. This one is a nice, stable process here, but it can involve some work too. That's just the fact of the matter. Okay, but let's go ahead and see how we can use Gaussian elimination rather than determinants to find a matrix inverse if it exists. Okay, I'm going to go ahead and we'll consider the following kind of a concrete example here. Okay, suppose A is the following 2 by 2 matrix. So reading across 1, 4, 2, 7, and I'm interested in finding A inverse. Okay, now we know by definition that A times A inverse should be the 2 by 2 multiplicative identity that I'm calling I2 there, 1, 0, 0, 1. Okay, this is a matter of definition. Okay, now suppose that I had the actual entries of A inverse written in the following way. B11, B12, B21, B22. There I'm using the double subscript notation indicating which row and column each particular entry is. Okay, remember the first subscript indicates the column the row that it's in, and the second subscript indicates which column it's in. Okay, alrighty. Well, anyway, let's say I gave it that name. I didn't want to use A's here because that's associated with A itself. Okay, so anyways, I call it B's. Okay, anyways, rewriting this statement up here like this, we're saying 1, 4, 2, 7 times this 2 by 2 matrix should be what? 1, 0, 0, 1. Okay? Now, if you think about how you multiply matrices, okay, take the matrix on the right and then starting on the column on the left in that matrix, you would multiply what? That column times that matrix should give you what? This column. And in the second column times the matrix on the left, okay, should give you the second or rightmost column of your product, okay, so that. All right, now I've just encapsulated those facts in these two equations right here, okay? So I broke this single matrix equation into two matrix equations where I'm just dealing with it, what, column by column, okay? So these each is implying the other here, just saying the same thing in two different ways. Now, when we see something like this, okay, remember that we could actually rewrite that. Okay, one way to think about that is to think about it in terms of Gaussian elimination. Okay, so if we were to write this in terms of Gaussian elimination, well, let's stop here for a second. See what the first line would be saying? If I multiply these matrices, I would be saying 1b11 plus 4b2 equals 1. Okay, that would be one equation. And then I'd have 2b11 plus 7b21 equals 0. Okay, and then writing those in terms of Gaussian elimination, we would have the following augmented matrix. 1, 4, dash line, right? 1. Okay, 2, 7, and then the dash line, and 0 on the other side. Okay, so these two are just saying the same thing in two different ways. This second setup is for Gaussian elimination. Notice that we have a similar situation right over here. The only difference between these two is what? Is the final column in each, the constant column in Gaussian elimination. Okay, the constant columns have changed. The submatrix to the left, the 1, 4, 2, 7, is identical in both cases. Okay, now remember, if we apply Gaussian elimination here, we're hoping to end with what? The row-reduced echelon form that's perfect for a unique solution 1, 0, 0, 1, right? The 2 by 2 identity matrix over here. And then what? The B1, and these would be numbers right here and here, right? These would be two numbers, okay? From what we see with the headings up here on each column, right here and here, we could see the answers would actually be over here, right? So ideally, we have what? 1, 0, B11, 0, 1, B21, okay? So we'd know the first column of our inverse. And likewise over here, only the difference being that we would have what? B12 and B22 over here, okay? Now, I'm going to just make this statement. Notice that we started with exactly the same submatrix to the left of the vertical dashed line, right? The 1, 4, 2, 7. Those are identical here. Okay? So exactly the same set of row operations would have to be performed in order to obtain the row reduced echelon form above. Okay? So we could combine the two separate augmented matrices into a single augmented matrix this way. Okay? So instead of just having a single column here like we usually do, okay, since we're actually solving two closely related systems of equations, okay, the only difference being what? The constant columns, the constants over on the right-hand side of the equal signs, in other words, we could actually combine them this way. So that looks pretty nifty, okay? So this is a nice compact way of writing it. And then if we can apply a Gaussian elimination, so the submatrix to the left of the vertical dashed line becomes the multiplicative identity, in other words, like we were saying above, 1, 0, 0, 1, then the first column would be what? The first column of the answer, and what? The second column would be the second column of our answer. In other words, the first and second column of what? A inverse that we were looking for. Okay? By the way, if this cannot be done, okay, if you can't do this, if you can't reach that stage, and I'll give you an example here in a minute, then A inverse does not exist. Remember, not every 2 by 2 matrix, or every square matrix for that matter, is invertible. Not every one is invertible. Do you remember the conditions under which it's invertible? Okay? A square matrix is invertible if and only if its determinant is non-zero. But we're not going to be talking about determinants other than mentioning that here. Okay, so this is a determinant-free method. Anyways, okay, let's go back to my original example. So I'm calling this example 1. I've got 1, 4, 2, 7, and I want to find A inverse if I can. Here's my setup. I go 1, 4, 2, 7. On the other, and I put a vertical dashed line. And on the other side, what do? I put 1, 0, 0, 1, the 2 by 2 multiplicative identity. Okay? And this is, yes, believe it or not, that says initial augmented matrix. Okay? Now what we want to do is use our elementary row operations, right? Gaussian elimination, to try to get it to, in order to get it to row reduced echelon form. Okay? All right. Now the first thing I notice here, I guess I didn't do it on this one. You notice that I would, remember we're trying to get towards 1, 0, 0, 1 over on this side if we can. I've got a 1, that's just what I want where I want it. Okay, so that's perfect, that 1 there. I don't like that 2 there. I want that to be a 0. How do I do that using legal moves? Remember the legal moves? You can what? Divide or multiply a row by a non-zero constant. You can interchange or switch rows. Or you could do what? Most importantly, add a multiple of one row to another row. Okay? So here's what I decided to do, since that's so perfect there. I'm going to go -2 times the first row and add it to the second row, and that will replace the second row. Okay? So this is my notation for doing that. Okay? Please adopt that. Okay? So I just go -2 times the first row added to the second row. The first row is not changing, so I just transcribe it. 1, 4, 1, 0. Okay? -2 times the first row added to the second. Got a 0 there. Yep, that's why I did it. That's why I chose that, because I wanted that 0 there. That's motivating everything. -2 times 8 is, or -2 times 4 is -8. Adding to 7, it gives me -1 right there. -2 times 1 added to 0, I got -2. -2 times 0 is 0, added to 1 is 1. So you see I end up with that matrix. Okay, now what do I want right here? I want right there that to be what? I want that to be a 1. Well, I'm almost there. I've got a -1, so I had to think of it either way you want. I'm just going to negate the second row, okay? And that replaces the second row. So -row 2 replaces row 2. So I multiply or divide by -1 all the way through, and I get 0, 1, 2, -1, and I've got that written right there. Now, this is perfect, isn't it? I've got a 1. That's just what I want where I want it, right? What don't I like about that column? I don't like that 4 there. Let's get rid of it. How do we do that legally? We're going to go -4 times row 2 added to row 1 replaces row 1. Okay? So I go -4 times 0 added to, well, I should say, hold on just a second. Just transcribe the second row since the second row is not changing. So 0, 1, 2, -1. Okay? -4 times 0 added to 1 is 1. Good. We didn't mess up the first column, right? That's what's so nice about Gaussian elimination. You do it right, you're not going to mess up previous columns. Anyways, -4 times 1 is -4. Added to 4 is 0. Yep, that's just what I wanted. -4 times 2 is -8. Added to 1 is -7. -4 times -1 is 4. Added to 0 is 0. Okay? Now, look on this side. Is that the multiplicative 2 by 2 identity? The 2 by 2 multiplicative identity, that is? It is. So it worked. What do you have on this on the right-hand side of the dashed line? You have the inverse. So the inverse is reading across -7, 4, 2, -1. And I just checked that by taking my original A matrix and multiplying it by this supposed inverse as a double check, and I indeed got 1, 0, 0, 1. Okay, you remember that multiplying matrices, I hope you remember that it's not commutative in general. Okay, so you might say, hey, maybe I have to turn this around and multiply them in the opposite order and see if I get 1, 0, 0, 1. No, there's actually a theorem that you're free to use. You don't need to prove it or anything. In fact, it's beyond the purview of this course. But inverses always commute. Okay, inverses always commute. So if I was to change the order of these two and multiply, I know I would still get 1, 0, 0, 1. Okay, so if it's an inverse on one side, it's the inverse on the other side. Left inverses are right inverses. Okay, all right. Now let's take another example here where it actually fails here. Okay, suppose B is 1, 2, -3, -6, and I want to find B inverse. Okay, if it exists, right? It doesn't always exist. Okay, so here we've got our setup, 1, 2, -3, -6. On the other side, we have the 2 by 2 identity here. Okay, this is what I want, where I want it, right? I love that one right there. So I'm going to go like this. 3 times the first row added to the second row replaces the second row. And I've written that here. So I'm indicating what I'm doing to somebody reading this. Okay, so the first row doesn't change, but the second row becomes what? 3 times 1 added to that gives me 0. 3 times 2 is 6. Added to -6 gives me 0. 3 times 1 is 3. Added to 0 is 3. 3 times 0 plus 1 is 0. And there we go. Oh, wait, no inverse exists. You notice what I have on this side? I've got just zeros here. Okay? You can think about this saying, 0, 0 times B1, 1, and what? B2, 1 is 3, and what? 0 times B1, 2, plus 0 times B2, 2 is 1. Well, that's impossible. Okay? Remember that situation? Well, forget this second column. Just think of it as a Gaussian problem. You see, remember here? If I've got zeros to the left-hand side of the vertical dashed line and non-zero on the other side, that's impossible. You're saying 0 is equal to 3. Okay? Or in this case, 0 is equal to 3. And there's some values where 0... anyway, you get the idea. Okay, no inverse exists. By the way, this is what's always going to happen if an inverse doesn't exist. Okay, using this method, you will end up with a row of zeros to the left-hand side of the vertical line and non-zero elements over here. Okay, that's what will always happen if no inverse exists. Okay, it'll always detect it. Okay, so this method will never fail if you're doing it right, but it will never fail to give the inverse or tell you that the inverse doesn't exist. Okay, And notice I didn't compute any determinants or anything to discover that. Okay? Now, I want to say that this setup works for larger square matrices too, so I'm just going to do one of these real fast. Here I've got this C reading across. I've got 1, 2, 3, 0, 1, 4, 5, 6, 0, and I want to find C inverse. Okay, so my setup's going to look like this. I've got C, right, to the left-hand side of the dashed vertical line. On the other side, it is what? The 3 by 3 multiplicative identity. You see I'm dealing with a 3 by 3 matrix. So on the right-hand side, I've got I sub 3. Okay? Now, this is set up. It's a pretty nice one here. I've got 1 where I want, right? That's perfect. It's what I want where I want it. 0, that's good. I love that. What don't I love here in this column? I don't like that 5. How can I get rid of that 5? I'm going to go negative 5 times the first row added to the third row replaces the third row. Okay? Then I've cleared out that column, so it's 1, 0, 0. Okay? 2, 3, 1, 0, 0. The second row didn't change either, so I've got 0, 1, 4, 0, 1, 0. Okay? The third row did change, so I've got negative 10 and 6 gives me negative 4. Negative 15 and 0 gives me negative 15. Negative 5 times 1 is negative 5 added to 0, and then the 0 and 1 carry through. So there's the next step here. Okay? All right? Now, looking here, here's why I want my pivot. I've got a 1 right there, right? And that's just exactly what I want, right? I'm trying to make it look like the what? As much as I can, the 3 by 3 multiplicative identity. Okay, I've got what I want, where I want it. Okay, what don't I like? I don't like that 2, and I don't like that negative 4. How do I get rid of that 2? I'm going to go like this. Negative 2 times the second row added to the first row replaces the first row, and 4 times the second row added to the third row replaces the third row. So what I did was actually just transcribe the second row, since it's not changing, but it is being used to change the other 2 rows. Okay? And I got 1, 0, negative 5, 1, negative 2, 0. Okay? And then the second row. And then 0, 0, 1, negative 5, 4, 1, when I completed these operations here. Okay? All righty, we're almost there. Okay, once again, this is a really nice one. Yes, this wasn't randomly chosen. Okay, this was chosen to be nice, to illustrate for you. Okay, I love that one right there. Okay? All right, I want to keep that one right where it is. It's perfect. Okay, I don't want to mess around with anything. Okay, I've got a 1 where I want. Okay, so this is my pivot. Okay, I don't like that negative 5, and I don't like that 4. How do I get rid of that negative 5 legally? Well, I'm going to use the third row, right? I'll go 5 times the third row added to the first row will replace the first row. So I indicated that there. I don't like that 4 there, so I'm going to go negative 4 times the third row added to the second row replaces the second row. Okay? Now, remember this operates, I guess I should have said this a long time ago. Remember, when I say the row, I mean the whole row, right? That means everything to the left and the right of the vertical dashed line. Okay? Anyway, so I went ahead and did that. Go through the arithmetic, and I got the following. So I've got the 3 by 3 multiplicative identity on this side. Perfect. That means my inverse exists, right? On the right-hand side of the vertical dashed line, I've got negative 24, 18, 5, 20, negative 15, negative 4, negative 5, 4, 1. And that 3 by 3 submatrix should be my inverse, okay? So let's see if I transcribed it correctly. I did, okay? And then what I finally did, just to check, I actually multiplied the 2 matrices. You can do that in either order, just as a check. And I indeed got the 3 by 3 multiplicative identity. Okay, so if you run some problems like this in your homework, you should be able to know how to do them now. Okay, I hope you understood that, and farewell.